Today I want to revisit the knowledge gap and how we define it, things like that. It's so simple to say, oh yes, we have a knowledge gap and this is what we've discovered and so on. But the reality is, what the hell is the knowledge gap? I mean, how do you identify one? And the simple answer is, it's an unknown, a complete unknown. And as students of science, researchers, or just keen thinkers, each of us will one day get to a point where we go, I just don't know what's out there. I just don't know what to expect next. And then we got to ask ourselves, well, how would we then find out what's out there? How do we do that? And that's sort of what I want to cover in this video, or at least try. The GERA Foundation presents this series called Navigating Research. Here's my version of a schematic of the progression of the knowledge gap from the complete unknown to the known. And you sort of imagine this as being, the known is basically questions on any physics exam or science exam or anything for that matter. Knowledge gaps do not have to be in science only, as you can imagine. But anyways, this is where everybody knows, and then I'm giving a test to an undergrad who has to come up with how to solve the problem, which has obviously already been solved. And a sidebar here is, when I was an undergrad, I knew this immediately. I didn't see it in this form, but I realized that all the tests I was ever given, all the homework assignments I was ever given, the answer must exist somewhere. So I would go to the physics library and I would find them. And that was a pretty simple way to do your work. Anyways, the known unknowns is where most graduate students get their PhDs from, master's degrees, whatever. And that's in the form of, we've discovered something, but we don't know what the hell it is. Basically, it's what it comes down to. And then someone spends their 4 or 5 years finding a way to explain it, or to explain the tool that will explain it, whatever. And then finally, there's the unknown unknowns, which a very small number of people really live in. I mean, for example, the discovery of pulsars would have sat down here initially because it was a complete unknown. No one expected to find it, and it was discovered by Lyndon Bell. And then eventually Hamish came along and explained what it is. That was her supervisor. And he was solely given, or was it solely? But he was given the Nobel Prize. She did not share in the Nobel Prize. I personally believe she should have. I think that the work would never have been done had she not discovered it. Or rather, it would not have been done had she not noticed it. And a good astronomer does that sort of thing. But they claim that she was given it because Hamish explained how and what the hell it was they were looking at, rather than simply making the detection of a periodic radio signal. Anyways, this is a schematic of the knowledge gap. This is not my creation of any kind. In fact, I'm going to give credit to an unlikely source, Donald Rumsfeld. And I'm not saying he created the ideas of unknown unknowns and all this stuff, but he's the one that I first heard it from, or I saw it in pop culture, or saw it on TV. And I think at the time, including myself, we all laughed at the guy. We thought he was a nut job. But as I thought more about the knowledge gap, it became very clear to me that it was precisely what it's all about. So I'm going to give credit to Donald Rumsfeld, who served in the George W. Bush presidency. Of all things, can you imagine?
Reports that say that something hasn't happened are always interesting to me, because as we know, there are known knowns. There are things we know we know. We also know there are known unknowns. That is to say, we know there are some things we do not know. But there are also unknown unknowns. The ones we don't know, we don't know.
There's a couple tools that are built into your genetics, first and foremost. And when I talk about tools here, I'm talking about tools that are going to get us across the knowledge gap. But remember, we don't know what the hell the knowledge gap is until we find something. Until we go to known unknowns, We know nothing. It's an unknown by definition. So, I mean, although it sounded crazy when you listen to someone like Donald Rumsfeld talking about unknown unknowns as it relates to the spy business, well, what he's really referring to is things like somebody deciding to sit at a desk and think about ways in which they can attack the U.S. For example, 9/11 by airplane. I mean, someone wrote a book about that. Somebody wrote a report about the possibility of that occurring. And yet everybody said, well, no, we had no idea. Well, somebody thought of it, but everybody else just downplayed it, deciding that it's completely ridiculous. That's what imagination gives you. They give you that possibility. It doesn't mean it's real. It doesn't mean it's out there. And when a scientist gets to this cliff at the cutting edge of science, it takes, first off, curiosity for them to get there. Okay? And now it's their imagination that holds them back going any further. In other words, if you want to push the frontiers of science, you want to go beyond the cutting edge of science, and you want to go into the great unknown through that knowledge gap, or find a knowledge gap for that matter, you got to have imagination. Full stop. So your two biggest tools to this whole business, to getting beyond and going over a knowledge gap, is curiosity and imagination. The third you want to have, or have someone around you with, is creativity, because you got to create the tools with which to test what's out there in the void, the great unknown. You got to do that. And a lot of times, I mean, I will spend a lot of my times thinking about things like that. I think about the tools with which we observe and how we can make them better, more efficient, which means we can collect more data, or we can observe in better ways, or we can observe in different ways. And that's sort of examples of the tools that we create so that scientists can come along and get across, or at least discover, a knowledge gap and get to the known unknown, where you discover something, but nobody knows what the hell it is. Okay? So that's what's called filling the knowledge gap. That's really what it takes. It basically starts with curiosity. It comes to the process where you get to an end point where you got to start being curious beyond that. And finally, it's creativity to find tools with which to prove your imagination was correct. Okay? That's what we're basically doing here. Here are some examples of the tools that astronomers would come up with to discover these knowledge gaps, these unknowns, and the unknowns, etc. Okay, so the two obvious ones, the oldest one is optical telescopes. They've been around since Galileo, right? What would that be? The 17th century, the 1600s. Radio telescopes are very new. They really only came into existence in the 1930s when they first discovered radio signals by Carl Jansky, and no one believed him. The optical people didn't believe him. My supervisor hated optical astronomers, just for an aside. But anyways, by the 50s it had become established. Radio astronomy became very established and accepted, and they were making some incredible discoveries as a result of this. Now, into the future, we've had infrared telescopes that are put in space, ultraviolet, gamma ray, etc., and Hubble, for example, is in space. Now we have the James Webb. Those are all tools with which we're going to use to make great new discoveries, and they always do. They always do. I have yet to see one now. There's other ways to do it, though. There's other ways. There's tools such as physical tools like these telescopes. There's also the back ends, the electronics that goes into it. But more importantly, just how we observe and what we're observing. So the techniques with which we observe are new tools in themselves, okay, which is where I spend more of my time. So anyways, these are examples of tools in astronomy. Every science will have its own tools. The microscope, okay? It goes on. Seismometers for earthquake studies, whatever. Okay, those are the tools that get them across knowledge gaps. I'm a radio astronomer who normally studies star forming regions, massive stars, much bigger than the sun. And the tools with which I use, because I normally work on single dish telescopes, such as the one here, this is Harder-Bierstock Radio Astronomy Observatory's 26-meter antenna, is I use spectroscopy, and I study what are called masers. These images here are basically time domain images of masers. A maser is a laser beam in space. It's basically a molecule is being excited by the energy coming from a massive star, and I can see the spectrum in a spectrogram, and that's These are what we normally look at, spectra. I call them squiggly lines. They're really quite boring to stare at day in, day out. Anyways, and the prettiest image I can create in my science is these dynamic spectra. I can give you nothing that looks interesting, okay? But anyways, with this particular tool, the spectroscopy, which is not mine created, we started monitoring masers associated with these massive stars, and we started discovering interesting phenomena. A good friend of mine discovered periodic methanol masers, Sharmila Goodhart, very good astronomer. Anyways, and here you can see what we discovered in 2015. We basically found that these masers suddenly got very bright, so they went through an accretion event. In other words, a star was there, it didn't have enough energy to form these masers, but suddenly it created a big blob of mass fell onto it and caused it to get a little bit bigger and have a huge burst of energy forming these masers, and we call that accretion events, okay? And at the same time I was doing that, some people discovered the exact same thing for this source using ULMA. So it was a really great piece of work, a great piece of serendipity, to be honest. And even more serendipitous, a second group discovered a similar event in a different source. So we were all very excited about this, knowing that there are these massive accretion events, and we had a tool with which to identify when they're occurring, and that is monitoring these relatively strong masers. So all these little single dish telescopes like Hart-Trail became valuable suddenly, where they weren't before, but he thought they could do no good science. Well, now we can use them to trigger bigger research experiments when we discover flaring events. So when these masers start getting brighter, it triggers other observations from other big telescopes, such as the James Webb, ULMA in the Atacama Desert, Andes, VLA in the US, EVN in Europe, and so on. So all of that was the result of two groups finding these accretion events. So its time domain science has led to this kind of, that was the tool that led to this kind of discovery. And of course that led to the creation of the Maser Monitoring Organization, a group of researchers and observatories around the world that coordinate efforts to look at more sources more often at more transitions, which should lead to more discoveries, okay? The 4 mores, all right? Now myself, I still do that. I still look at the variation in the flux, how bright they are in these colors. So red is bright, it's 2000 versus blue, which is near 0. I also want to look at how the velocities change over time. So I'm looking at velocity drift effect, that's what we call it, velocity drift. We found some interesting results in velocity drift, and some of which we're not sure we could even explain yet. So most of it might be very obvious, very simple explanations, but we don't know what it is. So our new tool is monitoring not only the flux, but seeing how the velocity changes over time. And we needed to develop new analytical tools to tease that information out, because the resolution is too poor to see it in simple images like this. Sometimes you can, honestly, but most times it's incredibly small and not reliable. Most people won't agree with it, won't believe it. Anyways, an example of velocity drift seen in the channels changing. Anyways, so my latest tools I'm developing to get across a knowledge gap, or first to identify a knowledge gap, is to monitor the velocity and then fit it with find very accurate measurements of its velocity peaks, so where those little lines are, the centers of them are, and then look at its line width and its strength, etc. So that's the new tool that I've come up with. Anyways, each of us will find our own new tools, but the most important tools I have, and all of us that do this have, is we are curious, we are imaginative, and we are creative. Those are the 3 things we need in order to identify and get over knowledge gaps, to find unknown unknowns and make them known knowns. One of the great knowledge gaps would have been standing on that pier on this day. Would you have gotten on that boat? The GERA Foundation will produce more videos like this. Please like, share, or subscribe if you enjoyed this video.